Okay, so for those of you that are in my first class section of the day, which is section 122, which is at 12:30, if you were in class, you'd recall that we sort of ran over time. We didn't get the chance to go through all the examples here, looking at the critical values for the z distribution, and so I promised everyone that I'd put up a short video sort of going over the last 10 or so slides. We're going to go over some of the ones we did in class again, just in a little more detail so we have time to answer everything. Okay? So, for the earlier slides in class, all the way up until this point, what we talked about was that we knew what the z-value was. We can calculate what the z-value is for some given value of some variable. And we wanted to find what the probability of that occurrence happening was. What's the probability that less than that value will occur, right? That's how the z-distribution works. That's how a table works when you're reading for a z-value. All right? Now, in some other cases, we know what the probability is, or we have an idea of what we want the probability of some outcome to be, and we want to find what z-value corresponds to that if it's a normally distributed random variable. Okay? So we define that value, the z-value that satisfies the probability that we're looking for, to be called the critical value of z, or of x, and we'll show how to get to x from z here in a minute. Okay, so this notation isn't super important, so don't worry about it too much and how it's going to look, but you can do it this way in Excel with the norm sin function 1 minus c. That'll get you the critical z-value for some probability that you're interested in. Okay, and again, we went over a few of these in class, but let's go through each and every one again just to make sure that A, we know how to read a z-table pretty well, both getting a z-value and going to a z-value, as well as sort of just a refresher to make sure we didn't miss any time. All right. So, for example, in statistical theory sense, not necessarily from a business setting, but what is the critical value of z at 0.025? Okay, so to find that, go to our z-table. We have to go to the, negative z-table, okay, with the negative numbers here on the left, and we have to find which one of these probability results is 0.025, I think is what it was. 0.025, okay? So I got to go in, find out where it gets to 0.025, or very close at least, and it looks like it hits it exactly at negative 1.97, right? No, excuse me, 6, negative 1.96, right here, negative 1.9, here's my 0.025, 6, negative 1.96, so the answer here would be negative 1.96. Okay, and that's the answer. That is the critical z-value, satisfying the probability to the left of some z-value is negative 1.96. So a z-value of negative 1.96 here on the curve, there is a 2.5% probability that some occurrence of some variable will happen to the left of that z-value, less than. Okay, so that's how we find it for 0.025, critical value of z at that significance level. What about 0.005, right? So let's go back to our table, find where 0.005 is, and that is 54, 52, 51. So we can see that there's a 0.0049 and a 0051, which is so it must be somewhere equally in the middle of these two. For calculations, I don't care. Okay, so basically the answer here, the proper answer, is negative 2.575, right? So it's in between negative 2.57 and negative 2.58, and I can see that it's equidistant. 0.0051 is the same distance from 0.0049 as it is from 0.005, so I'm splitting the difference in half. It's negative 2.75 in between these two. Now, when you're doing calculations or for something on the quiz or exam, I'm not going to be bothered if you use negative 2.57 or negative 2.58. I don't expect you to know when and how to separate these two. It's no big deal. I will have controls in my grading key to know that you used one or the other, so don't worry about it. So as long as it's one of these two, or if it's the one right in the middle, which is negative 2.575, that's okay. But anyway, I was looking for 0.005. It's somewhere between these two. It must be somewhere in this range of z values. Okay, so the answer for this one is negative 2.575, which is negative 2.57 or negative 2.58. All right, so that's that one. What about for a critical value of z at the 1% level of probability? All right, so I go back to my z table and find 0.01, or as close as I can get. And I have, it's really, really close right here. 0.0099 is super close to negative 2.33. Okay, negative 2.33 is very, very close to 0.01. So the critical value of z for 0.01 is negative 2.33. All right, moving on. What about 0.05? I already know this answer because this is commonly used, but let's look for it. Find 0.05 in the table. And here's another one where it's equally split. There's a 0.0505 and a 0.0495. I know for a fact that it's right in the middle, but you can see that it's negative 1.64 or negative 1.65. If I can scroll up and keep this on the screen, I can. So negative 1.64 and negative 1.65. 0.05 is right between those. So for this one, it's negative 1.645, right in between 4 and 5. Okay, and again, you could put either one. I don't care. Negative 1.6. Actually, for this one, you really should be using this because we will see this number a lot this semester. So this one I think you should know, and we'll understand why this makes more sense later in the semester, but this one should be rounded out to 3 for the 5% probability level, negative 1.645. Okay. What about 10? This is another one that should be rounded out to where it's supposed to be, again, because it's commonly seen. And that one is really, really close. It's negative 1.28. Okay, so if I go back up a little bit so you can see, here's the closest one to 10, 0.1, so 10%, negative 1.28. More. Okay, and again, we're taking the probabilities that we're given, or that we think that we're looking for, and we're backing out a z-value from that table. Okay. What about 0.45? Let's look for it on the table. Z is 0.45. 0.45. Okay, this one is 17 10,000ths out. This is 22, so it's much closer to this one. The answer should be negative 0.13. Whoops. Okay, negative 0.13. That's what the critical z-value is for a 45% probability. All the area under the curve to the left of negative 0.13 on the z curve is 0.45. 45% of all the possible outcomes. All right. What about 0.65? Well, if we go to our table, 0.65, if we understand how cumulative probabilities work in a curve, we know that if we get all the way to 0z from the mean, so again, a standard normal distribution has a mean of 0 and a standard deviation of 1, okay? If we go all the way up to 0, our probability is 0.5, and you can see that in the table here. Negative 0.0 is this first column, is 0.5 exactly, right? So we are no longer negative z standard deviations from the mean, now we're positive standard deviations from the mean if we're looking for a 0.65 probability. Okay, so I have to use my other table. Okay, using the other table, so we're looking for 0.65. Okay, so I can zoom in a little bit for you. So this one is 17 out, this is 20 out, this one's closer. It is positive 0.39 for 0.65. My mistake. 0.39. Positive z. This will give us 65% of all the possible outcomes of some random variable z will occur less than a z of 0.39. All right. So going back to the exact same example we had in class, talking about the human resource director and giving out the exam scores, analyzing them, trying to peg who's passing, who's failing, what have you. Same information. The mean is 20.68. Standard deviation is 2.96, and I'm assuming this is points of some kind, okay? Knowing that and knowing what we just went through, what cutoff value should she use, the human resource manager, for the passing score if she wants half of the applicants to pass? Okay, now we can look at the table. So basically this is a question of trying to find the critical value for the points required to pass of 0.5. Because if we want half the applicants to pass, we want, there's a curve here, it's drawn, so I'm going to use that. We want half of the applicants to do worse than that passing score, and we want half the applicants to do better than that passing score. And if half of them do better, half of them pass. Okay? So we're interested in what passing score we should use in order to make sure that half of the applicants are expected to pass. Well, without even having to look at the z-table and find what my critical value for 0.5 is, we know that since a standard normal distribution has a mean of 0 and a standard deviation of 1, if the mean is centered on 0, then we're already at 50%, right? Half of the probability outcomes are less than the mean of 0, and half are greater than the mean of 0. Now that's on the z. Translating that to the variable x, which is test scores, okay, the test scores, if she wants half of them to pass, what she has to do, she has to set the passing grade to be equal to the mean, right? If the passing grade is the average, if this is a normally distributed variable that's perfectly symmetric, then half of the applicants are expected to score less than 20.68, and half are expected to score more. And if half score more, half will pass. Okay, so that's the answer to this one. What cutoff value should she use if she wants 10% of the applicants to pass? Now this one's a little bit different. This isn't as easy. I guess I could prove the last example. So if I go to, I found 0.5 on my z-table, okay? It's 0.0. 0.0 z's, standard deviations away from the mean that it is the mean. Okay, and that's why the answer previously was the mean of the test scores that was given. It's 20.68 points. Okay, now we're asked to figure out what cutoff value we should use if we want 10% of the applicants to pass. If we want 10% of the applicants to do better than some score that we can set. Okay, so what that means, I think I have it drawn here. Yep. Is that, and forgive my drawing here because I'm doing this in Microsoft Paint with my mouse, and my mouse doesn't really like to be clean. So basically, this is the range on some variable x where students are going to, or applicants, excuse me, are going to score better than some cutoff value, some critical value of x sub c, okay? 10% are going to do better than that, all right? So we want to know what cutoff value we should use if we expect probabilistically 10% of people will pass. Okay? Now remember, when you're looking at a z-table, all of these values are the cumulative probability values, which means that it's the probability that something will occur less than some value of z to the left. Okay? And if you'll notice, the way this problem is set up, if we want 10% of people to do better, greater than some score value, we need to know what this probability is. And if this is 10% and the area under the curve is 100%, this must be 90%. All of this area up until that cutoff value, 90% of applicants are expected to fail if we set the score at this value. Okay? So that means we need to look for 0.9, 90%, in the z-table, and then get that critical z-value. Okay, so go by my z-table, and I'm looking for the positive z's because 90% is greater than 50%, so I'm positive z's away from the mean. I'm looking for 0.9. The closest to 0.9 is this one right here, which is 1.28. Positive 1.28 away from the mean. Okay? Positive 1.28 standard deviations away from the mean. Okay? That's my z-value. This is my z-value at which I should be setting the cutoff score for that exam. But what does that mean for the actual test score? How do I get to an x value, the value for that variable, from a z-value? Well, if we can get to the z-value, if we're given an x value using... I deleted it. Give me a second. Using this formula, z is equal to whatever x we're interested in minus the mean over the standard deviation of that variable x. Well, then just by rearranging this formula, moving things around to solve for x, this is a formula we can use. Okay, and this isn't a new or novel formula. I just rearranged this formula to calculate the z, to standardize the variable x. Now, I need to de-standardize the variable x, right? So that's equal to, this is z. X is equal to z times sigma, which is your standard deviation. Those two together, and then add the mean. And doing this will give you your value for x given some value for z. And if our value for z is lost, like it is right now, there it is, 1.28, okay? I just plug in 1.28 into this z area here and calculate what that x would be. And if I do that, I should get 1.28 times the standard deviation of, I think, 2.96. Somebody yell at me if I'm wrong. Plus the mean of 20.68. I should set, doing that, plugging in my z here, and then plugging in my sigma and my mu, I get 24.47. 24.47 is the passing score I should set if I want only 10% of the applicants randomly taking the test to pass. Okay? That's how you get to a critical value of x by backing out the probability from a z table, de-standardizing the z, and then finding your x value. Okay? Good thing is this is a video. I'll put this on YouTube, and you can go back and rework it yourself over and over again if it doesn't make sense. All right? So, knowing what we know then, what cutoff value should we use for passing if we want 75% of the applicants to pass? Okay? So by the same logic, oh my god, there we go. We know that we want 75% of the applicants to score better than some value, some test score. Okay? 75% will do better. If 75% pass, 25% don't. Right? And again, when you're reading a z-table or any cumulative probability distribution, it's always less than some critical value. So I need to look for a z value, which gives me 0.25, 25%. Okay? So that's going to be in the negative tables because 25 is less than 50%. Start looking for my 25, and 25 will put me... It's 14, this is 17, this is the closest, it's negative 0.67. Okay, negative 0, oh my god, 0.67. I am not used to drawing on a computer. Okay, that's my z value. My critical value of z is negative 0.67, at which 75% of applicants will pass with that score. But I don't have a score yet, all I have is a z value. So I need to de-standardize negative 0.67 to get the value that I need. All right, so let's do 0.67 negative times 2.96 standard deviation plus 20.68. I should set the passing grade at 18.70. I'll round out 18.70 if I want 75% of the applicants to pass, following all that logic we just followed. And again, if you lost yourself there for a second, you can back up the video and see where you lost yourself. Okay? Experience has shown the bottom third of applicants are unqualified, but the top third quickly leave for better jobs. So basically, there's 33% of applicants, 1/3, that will score low enough on some exam or the exam that we give, at the job. Of that exam that we give out, 1/3 of the applicants will score low enough to fail. Just fail, they don't deserve to work at the company, whatever. They go on to find something else. All right? But the ones that score in the top third end up being too good for our job, and they go out and they find other jobs somewhere else where they can maybe get paid more or get better benefits or whatever, right? So, knowing that, where we don't want the people who score too low, and the people who score too high, we're going to waste time and training money on before they decide to leave us anyway. What cutoff values of the exam scores should we use in order to find that middle third that we're interested in? Right? So, basically, I don't want to save that, go away. If I draw this out. Okay, so I have And this is not to scale, so do not think this is to scale. 33%, 33%. Wow, that looks awful. Just do that again. 33%. Okay? These guys fail. They're not good. These guys are too good. Oh my lord. Just too good. With a U, with an umlaut. There you go. Too good for us, okay? We want these people to stay at our company. And so based on the scores we get, we're only going to hire people who score between this value and this value on the test. Okay? So I need to know what those values are, right? So, like we've been doing for cumulative probability so far, if I want the probability of something in between something else, okay, I just need to find the probabilities of both of its boundaries as they go less than those boundaries. So this probability value, everything up to here would be 33%, repeating, of course. And this one, it's one third is covered by this area, another third is covered by this area, so this one is 66% repeating. Okay, so I need to find both of these values in the z table, and that will give me the z value for the low score, the lower bound of the exam score that I want, and this one will give me the z value for the higher exam score that I want, for the upper boundary. All right? So let's look for, I always look for the bigger one first, that's just me. Let's look for 66%. Both of these should be in the, well, 66 will be in the positive table. 66 gives a 66.4. This one's super close. This is actually almost the same. We'll just do the smaller one. It doesn't really matter. 0.43 for the lower bound. Okay. 0.4. Oops. 0.43 is my critical z value to satisfy a 66% probability. Okay, that's what the z value is. And again, 66% not because I want something that I don't want both of these, but this is the z value that is the top bound of this area, right? So yes, it does give me this area as well, both of these, but by finding this area as well, the next one, the 33%, that sets the lower bound. So all I'm looking for is these x values by finding these z values. So again, I know what the area is. I'm not looking for the area. I'm looking for the values that bound that area. Okay? So don't get confused by thinking, okay, well, why didn't I just do 33% one way, this way, there's area. Right. Don't worry about that in this context. You're looking for the actual values of the boundaries. Okay? So 66% right off the table. That value, this one right here, the upper bound has a z value of 0.43. Okay? And we can back that out first. So bound upper, that's the wrong one, upper, is 0.43, following the destandardization formula that I gave you, 0.43 times 2.96 plus 20.68, 21.95 points. I should have put points on all of these. Okay? That's the upper bound. That is the z value, the upper bound of this area that satisfies cutting off everyone except the top third, or including everyone except that top third that'll leave us for some other job. All right? So that's the z value of 0.43, destandardized using this formula, gets us to 21.95 points for our upper bounds. Okay, what about the lower bounds? Again, go to this, find 0.33 repeating as close as you can on the z table, and that will be negative 0.33, 85, 312, blah, 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 blah. This one is really close. This one is negative 0.43, and that's what you would expect. We found it anyway. But if you're looking for two z values that are exactly symmetric across the mean, so here's the mean, 0, right? This one is 0.33 away from 0, because again, it's a positive 0.33% from 0, but it's 66% from negative infinity. And this one, I'll draw a little line here. Okay, this one is the same distance away from 0, from the mean. And if that's the case, the z-values should be reflected symmetrically. So positive 0.43, excuse me, and negative 0.43. That 3 looks like trash. There we go. Okay, so by doing that, I have 0.43 negative times 2.96 plus 20.68, and that gives me 19.41. 19.41 points is the lower bound on how to keep that middle third of the applicants. Okay, so to answer this, you would say the middle third. Not this. I wouldn't ask you to format a question and answer like this, but basically the middle third of applicants are expected to score between 19.41 and 21.95 points, and that is how you would answer a question like that. That's the process you would follow. That's how you would solve it. Okay. That's all for the video, because that's all for the slides, I believe. Yep. So any questions at all, please do not hesitate to email me, visit office hours, go to SI, ask them questions. Take advantage of the resources you have, and I will see you all on Tuesday.